Good day everyone. Welcome to my channel Quick Tech Master Mariner. Don't forget to like, subscribe and press the bell icon to get notification of all other videos.
Alright, let's dive into a question about ships that seems super simple on the surface, but is actually, well, surprisingly deep. You ever see one of those massive container ships just gliding across the ocean and wonder, how fast is that thing really moving? I mean, it seems like a straightforward question, right? You'd expect an answer in miles or kilometers per hour, and that's that.
But, in the world of navigation, if you ask that question, you're likely to get another question right back. Which speed are you talking about? And that's because, get this, there isn't just one correct answer. There are two.
And those two answers, they really come down to one single crucial distinction: the difference between moving through the water and moving across the Earth.
So on one hand, you have what's called speed through water, or STW for short. That's how fast the ship is physically pushing itself through the water. And on the other hand, there's speed over ground, or SOG. That's how fast the ship is actually traveling across the planet's surface. Let's break down why that little difference is a really big deal. Okay, so let's start with speed through water. Think of STW as the ship's own effort. It's the raw speed being generated by its propellers pushing against the water. This is what a little device called a speed log measures. It tells you exactly how hard the ship is working, totally ignoring any help or hindrance it might be getting from the ocean.
Now, let's flip to speed over ground. SOG is the ship's true speed, the one that actually matters for getting from point A to point B on a map. This is the speed your GPS will show you. It takes the ship's own effort, that STW, and then it factors in all the external forces, like currents and tides. This is the number that tells you how quickly you're actually making progress on your journey.
So what is this big, unseen force that causes these two speeds to be different? Well, it's pretty simple actually. It's the movement of the water itself, the current.
Probably the easiest way to wrap your head around this is to imagine the ocean is just a giant conveyor belt. So if the conveyor belt is moving with you, that's a following current, your speed over ground is going to be higher than your speed through water. Makes sense, right? But if you're trying to go against it, your SOG will be lower. And if that conveyor belt is just turned off, no current at all, then the two speeds will be exactly the same.
Okay, this is all cool in theory, but why does it matter in the real world? I mean, why do navigators need to track both of these numbers? Well, it's because they're used for completely different and equally critical jobs.
And the practical split here is actually pretty fascinating. When it comes to avoiding a collision with another ship, navigators are all about speed through water. Why? Because every other boat is floating in that same moving river of water. So their speed relative to the water is what really matters. But if you want to calculate your ETA, your estimated time of arrival, then only speed over ground is useful, since that's what tells you when you'll actually hit your destination on the map.
All right, let's make this crystal clear with a super simple example. Honestly, seeing the numbers in action is usually the best way to get that aha moment. So let's say our ship's engine is pushing it through the water at a steady 12 knots. That's our STW. And for our example, let's say there's a 2-knot current in the area. First up, what if that 2-knot current is flowing in the same direction as the ship? Well, it's like getting a free push from behind. You just add them together. The ship's 12 knots of effort plus the 2 knots from the current gives you a speed over ground of 14 knots. The ship is literally covering ground faster than its engine is working.
But what happens if the ship turns around and heads directly into that same current? Well, now that 2-knot current is fighting against it. The ship is still pushing through the water at 12 knots, its effort hasn't changed, but the current is stealing some of its progress. So 12 minus 2 gives you a speed over ground of just 10 knots.
So, at the end of the day, what's the big takeaway for anyone trying to figure out how fast a ship is going?
It really just boils down to this simple idea. Speed through water is the ship versus the water. It's all about performance and engine effort. Speed over ground is the ship versus the Earth. That's all about actual progress and arrival times.
And that leads us to the final and most important point. A really good navigator doesn't just know the difference, they feel it. They understand the context. They know exactly which speed to look at to make the right call, whether that's avoiding another vessel or just telling the port when they're going to show up.
So the next time you're watching a ship from the shore or maybe tracking one on a map online, ask yourself, which speed am I seeing?
And which one actually matters more from where I'm standing? It's a simple question with a now not so simple answer. Thanks for watching.